So this is what we had derived till the last class. We had an optimum W value, optimum width value, optimum L by N value. So this is the optimum L by N value for achieving the minimum delay, and that's why I have written in the subscript as the minimum delay for the optimum W and optimum L by N. And it is a function of RC and RW and CW, right? So even L by N, optimum L by N is a function of RC, RW, CW. And of course, it depends on also on the normalized parasitic factor. If it is a folded design technology, so then in that case, it will be 0.5. Otherwise, it will be a conventional design technology will give me 1. And if I use this particular optimum parameters, and what should be the delay per unit length, the propagation delay per unit length for the wire with repeaters will be given in the form of this particular expression. Again, it's a function of RW, CW, RC, and then the normalized parasitic factor. Energy per unit length, it considers all the capacitance that are there for the end segments of the wire with the repeaters. So this includes the wire capacitance as well as it includes the parasitic capacitance and then whatever the input gate capacitance. Using this particular optimized parameter of W and L by N, we have arrived at this particular expression where the energy per unit length for achieving the minimum delay. Right, so note that this is the energy for achieving the minimum delay, and if I design the repeaters and then the number of repeaters, this is the energy per unit length we will be able to achieve. And this turns out to be this particular function where it is VDD square and CW multiplied by 1 plus square root of 1 plus rho in by 2. All right, so if I consider 0.5, I'll get this as square root of 0.75. So it turns out to be 86.6% more than that of the VDD square into CW. And CW VDD square is nothing but the energy per unit length for a wire without any repeaters. But with repeaters, I'll get this additional component especially for the minimum delay. So this additional component will be around 86% more. Right, hope this is just a summary of what we had studied earlier. Let's take an example here. So we have a long length of the wire and the resistance and then the capacitance per unit length of the wire is given as 200 ohms and then 0.2 picofarad per millimeter. The FO4 is given as 15 picoseconds for the repeater design. So in that sense, the FO4, which is nothing but for a unit inverter followed by the 4 other unit inverters, we will get the phi RC parameter as nothing but 15 picoseconds. So that is what is given here for that particular the chip design. So RC value turns out to be nothing but 3 picoseconds. And they have used the folded technology, so the normalized parasitic inverter factor turns out to be 0.5. So let's try to use those particular expressions which we had seen in the last slide, and then see what is the delay, the propagation delay per unit length of the wire. So this is nothing but a function of RW, CW and RC, and this is what we had derived earlier. So using this particular expression, if I put in the values of RW, CW as 200.2 picofarads per millimeter, and RC value as a product of RC as 3 picoseconds, we are going to achieve 40.88 picoseconds per millimeter. Now this is the minimum delay per unit length, right? Turns out to be 40.88 picoseconds per millimeter. If the length is 1 mm, so we can get actually the propagation delay of the wire with the repeaters as 40.88 picoseconds. All right, hope this is clear. Now, if I want to find out the delay of the wire without any repeaters, delay of the wire without any segments, without any repeaters, in that sense, we will get, I shall be using these two parameters because that is the characteristics of the wire itself. And so the TPD, right, for the wire with no repeaters, for the wire only, right, will be nothing but RW, CW. And these are per unit length parameters, so I'll have to do an L square. So that will be the TPD, and then if I do a divide by L, so that I need to compare with this, then I'll have to do a divide by L. So if L is actually 1 mm here, So in this particular case, so TPD for 1 mm for a wire with repeaters, right? So this is an expression for the achieving the delay for the repeaters. It turns out to be 40.88 picoseconds. So in this particular case, if I do that, I will actually achieve 40 picoseconds. Right, so if I calculate this TPD of the wire per unit length, I'll get RW/CW multiplied by L. L is nothing but 1 mm, and so this will be 200 multiplied by 0.2 picofarads. That will be 40 picoseconds. And if L is equal to 1 mm, I'll get the TPD as nothing but 40 picoseconds. Right, compared to that of 40.88 picoseconds. All right, hope one should be able to understand, if without the repeaters what is the delay, and with the repeaters what is the delay. Now let's try to understand what is the repeater spacing. So it is nothing but if we have n-1 repeaters, I will have n segments. So I need to find out what is the spacing between the n segments, right? Or rather the length between length for each of the segments. So the length of each of the segments is nothing but the overall length of the wire divided by the n segments. So that is anyways given by an optimized expression. Here it is 2RC into 1 plus rho in by RW/CW. RW/CW, the parameters are given 200 ohms per millimeter and CW as 0.2 picofarads per millimeter. So that is given from this particular data. So moving ahead, RC is nothing but FO4 is given. So I should be able to find RC, and that it turns out to be 5 or rather 3 picoseconds here. So 2 multiplied by 3 picoseconds and then 1.5, because this is the folded design technology node, divided by 200 multiplied by 0.2 picofarad per millimeter and millimeter here. So I will eventually get 0.474 millimeter as the spacing between the segments. And if the length of the wire is actually 1 mm, then we know what should be the number of segments here. The number of segments turns out to be, for an L of 1 mm, I'll get n as nothing but 1 mm divided by 0.474 mm, close to nothing but 2. And remember that the number of segments here, so that I need to introduce the n-1 repeaters or the inverters in this particular case, that has to be a whole number, right? That cannot be a decimal number. So that cannot be a real number. That has to be an integer. So in this case, the number of segments has to be, it will turn out to be 2 point something, but it will be rounded off to 2. So I will have to insert I will have to make 2 segments. So that means I need to insert 1 inverter or 1 repeater for a length of 1 mm. All right, hope that is clear. Optimize width of the repeater of, if I'm using, if we have a length of 1 mm, then the number of segments is 2. So the number of repeaters I need to add is 1. And what should be the width of that particular repeater? And that is given by this particular expression, right? RW and CW. The FO4 is actually given as, so if I go back, the FO4 is given as 15 picoseconds. RW and CW are given, but I don't really know what is the R value and what is the C value, right? So what I'm going to consider is for a unit inverter, this is always for a unit inverter. We know that the switching resistance for a unit inverter is close to 10 kilo ohms. Unit inverter means I will have the PMOS and then the NMOS design. This is a VDD and then this is the ground rail. So this particular W is nothing but 200 nanometers. This is nothing but 100 nanometers. And according to the short channel, this turns out to be, or even this one, right? Turns out to be somewhere around 10.7 kilo ohms. So we just for our own simplification, we consider the switching resistance to be 10 kilo ohms. The capacitance, we consider it to be, for the 3C capacitance here, which is nothing but 0.3 femtofarads, where 1C, the unit NMOS transistor's capacitance was considered to be 0.1 femtofarad. So 3 times that will be considered for the unit inverter. So we'll consider 0.3 femtofarads, which eventually turns out to be RC value is equal to nothing but 3 picoseconds. So if I use that particular R and C values here, so this R value goes here, this particular C value goes here, we know what is CW, we know what is RW, we should be able to find out the optimum width. Turns out to be 182.57, the scaling factor. Now remember that the W is still a scaling factor. It is not an absolute number, it's not an absolute unit. So to find out the absolute width of the repeater or the inverter which we have been using here, it is nothing but the NMOS width should be nothing but 182, that is the scaling factor, 182.57 multiplied by the unit inverter's NMOS width. The unit inverter's NMOS width is nothing but 100 nanometers here. So if I need to scale it by 182.57, the overall absolute dimensions of the width of the NMOS transistor turns out to be 18.257 micron. Right, so 182.57 multiplied by 100 nanometers, or also call it as 0.1 micron. So we will get 18.257 micron. PMOS width has to be 36.514 micron. So the one inverter or the one repeater which we are using for a 1 mm long wire, we need to have the width of 18.257 micron and 36.514 micron. Right, hope this is clear. Moving ahead, energy per unit length, for one bit of information that has to be transferred across, right? So if I have a long length of the wire, right, A to B, and I need to have one bit of information that is to be passed, so 0 to 1, that has to be passed to the B, 0B, 0 to 1. So that is what is called as, for passing one bit of information, what is the energy per unit length of the wire? Right, so it turns out to be the expression is 1.866 CW into VDD square, coming from row inverter as 0.5. So if it is a value of 1, it will be different. This particular, the value will be different. But we have considered the normalized inverter, parasitic inverter using the folded technology design as 0.5. So we will get 1.866 CW VDD square. So it will be CW turns out to be 0.2 picofarads per millimeter. So multiplied by 1 square, because this is a 65 nanometer technology node. And typical values of VDD is nothing but 1 volts. Right, so we'll get energy per unit length as 0.3732 picojoules per millimeter. This is for sending one bit of information on the other side of the long length of the wire with the optimized number of repeaters. Right, and with the optimized width of the repeater. Right, so this is the energy that will be consumed. Right, if it was only for the wire without the repeaters, right, if it was only the wires without the repeaters, so the energy per unit length for the wire only, right, turns out to be CW VDD square, right, which will be nothing but 0.2 picofarad per millimeter multiplied by 1 square. Right, so it will be nothing but 0.2 picojoules per millimeter for sending one bit of information. Right, but with adding the repeaters, making it an optimized number of repeaters and an optimized width of the repeaters, so that we'll get the minimum delay, the energy that has been compensated is actually more than 0.2. So it is 86% more. So here it is getting 0.37, here it is actually 0.2. So one has to realize that, to improve the delay, the energy is kind of compromised. Right, so what we had seen earlier is, just an example for a long length of wire, and for getting the optimized design so that we will have a very less delay, what we are compromising is on the energy. Right, we are giving 86% more amount of the energy. So there is one more design factor or design fitness we call, and that is called as making our designs, the number of repeaters or the number of the size of the width of the repeater, catering towards the product of energy and delay. So that's what it is called as an energy delay product, and also termed as EDP, right? E from the energy, D from the delay, and then P from the product. Right, and this is kind of a standard, well accepted, kind of very popular design fitness parameter catering to the digital VLSI design. The other parameter is of course the delay. That is also considered as one of the fitness parameters. Energy is one of the fitness parameters. Footprint or the area is considered as another footprint, the fitness parameter. And another fitness parameter is the energy delay product. So if I consider the energy delay product for a wire with the repeaters, right, we will have energy multiplied by delay, and that has to be optimized now, or that has to be minimized, so that we'll get the optimized parameters of W, we'll get the optimized parameters of L by N, and then we should be able to extract what is that propagation delay per unit length of the wire for getting the minimum energy delay product. And then similarly, we will try to find out what is the energy per unit length of the wire with the repeaters for getting the minimum energy delay product. Right. So what we had calculated earlier, or what we had estimated earlier, was the propagation delay per unit length as well as the energy per unit length, the optimized width, and then the optimized L by N, catering towards the minimum delay. Now the same parameters we will try to extract for catering towards the minimum energy delay product. Right. So hope that is clear. So the energy delay product is nothing but the product of energy and delay. So I should be having an expression for the energy here. Right, I'm assuming the VDD is nothing but 1 volt, so I'm not written 1 volt square. So I'll just write it as VDD square. This is the number of capacitance we have for the N segments of the wire. Right, so if I have a long length of the wire and then make it into N segments, each segment has this particular capacitance. Right, so this is nothing but the wire capacitance, and then this is nothing but the parasitics plus the gate capacitance of the next repeater. And if I multiply by N, I will get the overall capacitance of the long length of the wire. And multiplied by, this is the Elmore delay for one segment of the wire. And multiplied by N, we will get for the N segment. So that means that it caters towards the overall delay of the length of the wire. And so once we have the EDP expression, and to optimize the EDP, or rather to minimize the EDP expression so that we'll get the optimized W values, optimized L by N values, we will use a similar differential method. So the first order differential of EDP with respect to N is nothing but 0. So we will get L by N expression for L by N, the optimum expression for L by N for getting the minimum EDP. It turns out that for the L by N, the optimized L by N for achieving the minimum EDP is nothing but 1.7 times the L by N expression which we had got for achieving the minimum delay. All right. So if this particular expression we know, which is nothing but square root of 2RC into 1 plus the normalized parasitic factor divided by RWCW. So the L by N, optimized L by N for achieving the minimum EDP turns out to be 1.7 times more than that of the L by N, that the optimized L by N that we have achieved for the minimum delay. So this is 1.7 times more, right? So if I have a long length of the wire, right, let's say that the length of the wire is actually 10 mm. Right, so the number of repeaters, the number of optimized repeaters, right, that I will achieve for the minimum delay here, minimum delay, right, will be nothing but so the number of optimized parameters for the, so this L by N will give me the number of the spacing, right, the number of the length for each of the segments. Right, because N is nothing but the segments. So N optimized segments that has to be created for a 10 mm long wire, right, to achieve the minimum delay will be nothing but, so whatever is its value, L by N value. So I will have 10 mm divided by whatever is the L by N that is been with the optimized parameter of L by N for the minimum delay. All right. So I'll get some particular value. So if it is L by N as per the previous example, if it was 0.45 or something, so I will get N optimum for the minimum delay. It turns out to be 10 divided by 0.454, slightly above the value of 20. So we need 20, more than 20 segments. So that is what we will have. Now if I use, if I try to find out the number of segments for achieving, so the optimized number of segments for achieving the minimum EDP, right? It turns out to be, and for the same length of the wire, so 10 mm divided by the L by N for the minimum EDP, which is nothing but 1.7 times L by N for the minimum delay. So that is what the minimum delay, that is what we had achieved, right? So if L by N for the minimum delay was turning out to be 0.454 or something like that, so in the denominator we have 1.7 more multiplied by 0.454. So the optimum number of the segments that we will create for achieving the minimum delay turns out to be less than that what we have acquired for the number of segments, optimum number of segments for achieving the minimum delay, right? So for achieving the minimum EDP, the number of segments as well as the number of repeaters will turn out to be less than that of whatever we have achieved for the number of repeaters or the number of segments that we require for the minimum delay, right? Because this 1.7 parameter is coming into the denominator side and then will reduce the optimum repeaters, right, for achieving the minimum EDP. So hope this is clear and this will be kind of useful somewhere in our design analysis. That was about the optimized L by N parameter. Now let's have a look at what should be the optimum W parameter, the width of the repeater, and for doing that we will take the first order differential with respect to the W parameter, equate it to 0. Turns out that for achieving the minimum EDP, it should be 0.6 times less the width of the minimum delay, right? So whatever we achieve for the minimum delay, optimized parameter for the W for the achieving the minimum delay, it turns out to be 0.6 multiplied by that particular W value. So it turns out to be 0.6 square root of RCW by RWCW. So whatever we had achieved earlier in our previous example of 185.7 something, so 0.6 times, so it will be actually the width of the repeater should be less. And intuitively it makes sense because if the width is less, the capacitance is going to be reduced, and that reduced capacitance is likely to have it's likely to reduce the energy term, right? So this particular energy delay product, there is an energy term, and not only the delay, only for delay we need to have this W parameter, because there is a we are trying to optimize or we are trying to minimize the product of energy and delay, and that's why the width of the repeater that we are using has to be reduced. It turns out that it has to be reduced by 0.6 times. All right. So if now I have the optimized W and optimized L by N for achieving the minimum EDP, what should be the delay? What is the delay per unit length, right, when we have designed our repeaters and then the number of repeaters for achieving the minimum EDP, right? So if I put these particular parameters, 0.6 and then the L by N, which is 1.7 times the L by N for the minimum delay, and so the similar way what we have done it for achieving extracting the delay per unit length for the minimum delay parameters, so we'll use the same thing, but just that we will change here the minimum EDP point, right? So L by N and then L by N here and then W here and then W here. Now this one we'll put it for the optimized parameters for achieving the minimum EDP. So it turns out that the minimum, the delay per unit length for the achieving the minimum EDP turns out to be, so I've written here the expression for the L by N, expression for W, expression for L by N here, expression for W here. And so if I carry forward, I'm likely to get a 3.732 square root of RWCW, which is nothing but 1.14 times TPD, the delay, the propagation delay for the minimum delay per unit length. So it is actually turning out to be 14% more, right? So if I want to actually design my repeaters and then the width of the repeaters as well as have the optimum number of repeaters for achieving the minimum EDP, then it will give me the delay which is 14% more, right? 14% more than that of whatever the design, the optimized design which will be giving us the delay per unit length, right? So if the delay has increased 14%, right, then the energy has to naturally decrease, right? Because we are trying to achieve the minimum EDP point, right? The product of energy and delay has to be minimum. And that's where we have extracted the optimized W and optimized L by N. So in that case, the energy for per unit length for the minimum EDP point, so we'll try to calculate that, which is nothing but N by L and then all the capacitance here, VDD square. And here the W parameters could be optimized. We can put the W optimized parameters for achieving the minimum EDP. The optimized L by N parameters for achieving the minimum EDP. And so if I do that, I'll get 1.3056 CW VDD square, which is significantly less than that of 1.866 CW VDD square. Turns out that it is 70% of 1.866. So 30% reduction in the energy, 14% increase in the TPD, but 30% reduction in the energy. So overall, the product of energy delay turns out to be actually less. Right, and it also turns out that 30.56, if I compare 1.3056 with that of the wires with no repeaters at all, it will be CW VDD square. Right, so it is only 30% more than that of the unrepeated wire. Right, whereas if I consider this 1.866, right, so it is 86% more. Here it's 30.56% more. Right. So hope this the minimum EDP point, the important point that to be noticed or that to be observed is while we are achieving the minimum EDP point, the delay will increase slightly by 14%, but the energy of the designs of the number of repeaters and then the width of the repeaters, it will give us 30% reduction from the 1.866 CW VDD square. Moving ahead, so if I want to find out what is the energy delay product, right, per length square I have written because it becomes easier in our calculation. So energy delay product for for the minimum EDP. So it is nothing but the energy, the minimum energy, the energy while achieving the minimum EDP point per unit length, and then the delay for the achieving the minimum EDP point per unit length. It turns out to be 1.3056, whatever we have calculated earlier, multiplied by 1.14 TPD for the minimum delay per L. So it turns out to be, if I do multiplication, I'll get 1.48 CW VDD square, TPD, whatever is the TPD for the minimum delay divided by L. And if I want to find out the product of energy and delay for the minimum delay per L square, it turns out nothing but energy, whatever we have achieved for the minimum delay multiplied by TPD minimum delay divided by L and divided by L for both the terms here. So the energy for that we have obtained for the minimum delay is nothing but 1.866 CW VDD square and multiplied by TPD minimum delay per unit length. So this factor is 1.866, this is 1.48, and naturally this 1.48 will be less than that of 1.866. And that's indeed what we have, in this particular slide, what we have validated is the energy delay product for the minimum EDP or the designs, whatever we have created for the minimum EDP turns out to be giving the lowest EDP, right? When we compare that with that of the minimum delay parameters, right? So the product of the energy and the delay for the minimum delay parameters turns out to be 1.866 and then the other parameters, but here it turns out to be 1.48, so naturally it is less.